Hey folks, in this video I want to talk about wave diagrams and refraction. So, the important thing here is how do we represent light when we do care about its wave nature. So representing light as a wave rather than a ray. And wave diagrams are going to be the way we do this. We have two options. Option one is we can draw in our ray still, that's our ray of light, and then draw in lines that represent wave crests, so the peak of the wave. So that's one option for representing light as a wave. The other option is that we can draw the wave crests really big. So we can draw our wave crests like this, and then we can draw the directions those wave crests are moving as little chevrons or arrows on those wave crests. So these are our wave crests. So these are two ways to represent wave or light when we care about the wave nature of light. And in particular, I want to talk about how to draw both of these options when light refracts as it changes mediums. So, refraction. Let's say we have two mediums. On the left is air, and on the right here is glass, which I'll represent using the highlighter here. Let's finish coloring in quickly, I hope. Boom, that's glass right there. All right, this is N2, air is N1, and glass has a higher index of refraction. Great. So, anyways, let's say we have some incident light, some light that's coming in at an angle. So that would be our light ray that we would draw. And we want to know how it refracts. Well, it refracts. We need to draw on the normal line if that's what we're going to do, because we're always measuring relative to the normal line. And that light is going to, let's see, using my toy car model, which wheel is going to, this right wheel is going to get caught on the slower medium first. And so it's going to bend toward the normal like that. And I want to draw it. There we go. So our theta 1 with the normal and the incident light is greater than our theta 2 with the normal and the refracted light. But what we care about here is the wavefronts. That's the new piece of information that we're dealing with today. So to draw our wavefronts, we just draw lines into our light. Not so bad. But here's what we got to keep in mind is what happens to waves whenever they enter a slower medium. The frequency has to stay the same. The incoming rate of waves per second has to stay the same. And since the light is slowing down, that means our wave crests get bunched up in the slower medium. So you need to make sure you're drawing your wave crests closer together inside the medium, because they get bunched up as the light slows down so that we can keep the frequency the same. And then the reverse would be true if we're going in the other direction. The waves would get more spaced out if we were going from more optically dense into a less optically dense material. So that's how we would draw it with the rays with wavefronts. What about the other option here? We draw on the wavefronts as really big lines. How would we represent refraction in that case? Well, let's draw the same situation, light entering glass at an angle. All right, so there's our glass. Here's our boundary. And the light's coming at an angle, but now we're drawing wave fronts, really big wave fronts, like that. And we'll draw in the direction arrows on those wave fronts. And now our light still bends toward the normal. So that propagation direction is, I'm going to draw on a dashed line real quick, going to go from here to like that. It is going to refract still. So we need to draw in our arrows something like this. And if we do that well, we should naturally see that the wave fronts get more bunched up. It's a consequence of needing to match up our lines at the boundary. So we should see that bend very clearly. All right, so those are the two representations for drawing light as a wave and what refraction looks like in those representations.